Hello student, hi, how are you? Fine, good morning. So today we are going to see the next topic, that is for what, that is about the calculations of what, calculations of thermal equilibrium concentration of electron and hole. Okay, so thermal equilibrium concentration of electron and hole, and in last class we have seen what, we have seen the equilibrium distribution of charge carrier within the semiconductor, that is the equilibrium concentration of electron in conduction band and equilibrium concentration of hole in valence band. Okay, so that we have seen in the last class. Okay, so now today we are going to what, today we are going to see the equation for thermal equilibrium concentration of electron and hole. Okay, so we are deriving these equations for both electron and hole under thermal equilibrium condition. Okay, so let us see now thermal equilibrium concentration of electron and hole. Thermal thermal equilibrium thermal equilibrium thermal equilibrium concentration thermal equilibrium concentration of electron and hole. Okay, electron and hole, thermal equilibrium concentration of electron and hole. Okay, electron and hole, under the assumption that we will take some assumption here. What assumption we will take? We will assume that the effective, what, the Fermi energy level. Okay, we will assume that the Fermi level. Okay, under the assumption, under under the assumption that under the assumption that Fermi level Fermi level lies within within energy energy band gap. Okay, within energy band gap. So this is our assumption. Okay, this is our assumption. So under this assumption we will now find what, we will now find the thermal equilibrium concentration of electron and hole. Okay, so now first of all we will see for what, for thermal equilibrium concentration of electron, for thermal equilibrium concentration of electron. Okay, so now thermal equilibrium thermal equilibrium thermal equilibrium equilibrium concentration thermal equilibrium concentration of electron. Yes, concentration of electron in conduction band. Okay, in conduction band. So now see here, thermal equilibrium concentration of electron in conduction band. As we know very well, the distribution of what, as we know very well, what, total number of what, total number of electron in conduction band, how many? So that is what, n of e. Yes, this is actually the distribution of electron in conduction band, which is given by the product of what, product of density of state. Yes, density of state function in conduction band into Fermi direct distribution function. Yes, into Fermi direct distribution function. That is our equation number 1, that we know very well and that we have done in the last class. Okay, so now see here, this is what distribution of electron in conduction band. Now we are going to find what, total number of electron, what, thermal equilibrium concentration of electron. Okay, so that can be what, that can be found by integrating this equation. Okay, integrating this equation over what, over entire conduction band energy, then we will what, then we are able to find what, total number of electron per unit volume, where in conduction band. Okay, where in conduction band, this is what n naught is what, total number of electron. Okay, total number of electron in the conduction band. Okay, per unit volume. So it is also a what, thermal equilibrium concentration of electron in conduction band, which is nothing but n of e into d of e. Okay, n of e into d of e. Now as we know very well, that is what GC of E into F of E. GC of E into F of E, GC of E, GC of E into F of E. Yes, into F of E into DE into DE. Okay. So now see here, this is what density of state function in conduction band. This is Fermi direct distribution function. Okay. So now see, in conduction band, in what conduction band? See, this is my conduction band. Yes, and somewhere here it is valence band. Here is valence band, and in between this there is a what Fermi level. Okay, somewhere in between EC and EV, EC and EV. Okay, so now if you see here, these are what, these are energy state in conduction band. These are available energy state in conduction band, available energy state in valence band. Okay, valence band. Now when the electron is there in the conduction band, when the electron is there in the conduction band, when this energy, when energy level, what, when energy level is greater than EC, this E, this is my available energy state. Okay, energy level, this is greater than EC. Okay, so then we are able to find what, electron is present in the conduction band. So upper limit of what, upper limit of this conduction band is what, conduction band, it is not a real means this much conduction band. Means conduction band means free space, means free space means what, here free space means interatomic space within the crystal. Okay, so conduction band here it is indicating what, it is indicating interatomic space. Okay, interatomic space, like this is my crystal. Okay, let us say this is our what, crystal, this is my silicon crystal. Okay, so whatever the space is there, this space, this empty space, what is this, this is interatomic space. Okay, interatomic space. So this means what, conduction band. Okay, conduction band. So how many, so what is upper limit? Upper limit, we can say upper limit it can go anywhere in this. Okay, because there is what, upper limit means how many place should be there for existing of electron in the conduction band. It is like a free space. Okay, it is like free space inside the crystal, not outside the crystal. Free space inside the crystal is nothing but interatomic space. So its upper limit is what, infinite. Upper limit it will go to infinite, and lower limit if you will see what, EC, lower limit is EC. Okay, lower limit is EC. Then after that, let us just put all these value of GC of E and F of E. This is what, density of state function. If you will put this value here, this is from 0 to infinity. This is nothing but, this is from EC. Yes, EC to infinity. And GC of E is nothing but what? GC of E is nothing but 4 pi into 2mn star. Just wait. Yes, so this is what, 4 pi into 2mn star. Okay, 2mn star to the power 3 by 2 divided by what, h cube, divided by h cube into what, here square root of E minus EC, square root of E minus EC into what is this, Fermi direct distribution function is nothing but 1 by 1 plus e to the power E to the power E minus EF. Yes, e to the power E minus EF by KT. Okay, by KT into DE. Okay, so this is what, this just we have give down all this value of for this Fermi direct, for this density of state function, and this is Fermi direct distribution function. Okay, so just now we have to integrate it. Okay, so first one thing is there, let us assume that what, E, if we see this energy level E, this E is greater than what, EC. Yes or no? This energy level E, energy state, this energy level, this is greater than EC. Then from here, what you can say, here EC, if you see this EC minus EF. Okay, let us take the assumption that if EC minus EF is what, much greater than KT, much greater than KT. If EC minus EF is much greater than KT, then we can say that E minus EF is automatically what, much greater than KT. Then it is obvious that E minus EF is also much greater than KT. And under this condition, we are able to approximate this Fermi direct distribution function to Boltzmann approximation. What? Boltzmann approximation. Boltzmann approximation. Yes, Boltzmann approximation. We are able to what? We are able to approximate, okay, this as Boltzmann approximation. Okay, so Boltzmann approximation means if this condition is valid, then what? Which implies that e minus ef by kt is much greater than 1. Yes, now we can neglect this one from here. Okay, so we can neglect this one from, okay, from this denominator. Then what is the condition? Now n naught is equal to integration ec to infinity. Okay, 4 pi 4 pi into 2mn star 2mn star divided by h square to the power 3 by 2. Just make it as h square, it will come inside this. Okay, so now if you see here, this is my e minus ec. Okay, so then it will, now if it is greater than what, 1, then it will become 1 plus what, 1 plus e to the power e minus ef by kt. It is approximately equal to e to the power e minus ef by kt. Yes, if this condition is valid. Okay, if this condition is valid, now we can write it as, it will go upside. Okay, so now it is what, e to the power e minus ef by kt into d. Okay, under what condition? This condition. Okay, e minus ef is much greater than kt. How much greater? You can say e c minus ef is approximately greater than or equal to 3 kt. What? 3 kt exactly. How much greater? If someone will say how much greater, then you can say this much greater. How much greater? This much greater. 3 times of this, thermal voltage. Yes, 3 times of this. At room temperature, if you will see, at room temperature, like at 300 degree Kelvin, you will get this ec minus ef is approximately equal to 78 millivolt. Yes, 78 millivolt. Okay, how much greater? 78 millivolt greater. If it is at least above this. Okay, if this distance, what, if this gap is at least what, around, if this gap is at least around 70 what, 78 milli electron volt. Yes, if this gap, which gap? ec minus ef gap is at least how much? 78 milli electron volt. Okay, 78 milli electron volt. Okay, so then Boltzmann approximation condition is valid. Okay, so this is valid only when this gap is this much, under what? Under room temperature. Okay, under room temperature, if this condition is valid, then only you can do, otherwise not. Okay, otherwise you have to deal with this factor only. Okay, you have to solve this. This is only possible when this condition is valid. Which condition? ec minus ef is greater than equal to 3 times of kt, thermal voltage. Under room temperature, if you see, under room temperature, ec minus ef is how much? 78 milli electron volt. So therefore, if this gap ec minus ef is at least 78 milli electron volt under room temperature, then only we are able to take this Boltzmann approximation. Okay, then only we are able to take this Boltzmann approximation. If this condition is not satisfying, then we have to deal with this equation only. Okay, we have to deal with this equation only. We can't take this Boltzmann approximation. Okay, if it is not satisfying this condition. Okay, so remember, this is very important point here. Okay, so everything is fine except this. Okay, you have to be attention at this point. Okay, when it is valid. Okay, so that's it. Now we will further we will go. Okay, so now see this much. Okay, now we will okay, I will rub it here from here. Okay, so let us see. Everything is clear why we have taken this Boltzmann approximation. Okay, so now see here. Now come to n naught is equal to, let us take this upside, we will get what? Integration 0 to integration ec to infinity, integration ec to infinity. Okay, so then it is 4 pi 2 mn star, 4 pi 2 mn star divided by h square to the power 3 by 2. Okay, to the power 3 by 2 into what? Into ec minus f. Okay, so let us write here square root of ec, square root of e minus ec, e minus ec into e to the power what? Minus e to the power minus e minus ef by kt. Okay, Boltzmann approximation that we have taken. Okay, so we have assumed the condition that what? 1 plus e to the power e minus ef is much greater than kt. How much kt? ec minus ef is greater than, much greater than kt means how much? It is at least 78 milli electron volt. Okay, under room temperature, or in general it is 3 kt, it is 3 kt. Okay, so now see here, n naught is equal to, n naught is equal to, just do one thing here, just put this what? Put this eta. Okay, eta is equal to e minus ec, e minus ec by kt. Just put this eta is equal to e minus ec by kt, ec by kt. Okay, so then what? d eta is equal to what? de by kt, de by kt. Okay, so now see here, de is equal to what? de is equal to kt d eta. Okay, so kt d eta. Now just plug this value here. Okay, eta value here. Now before plugging this value into this, what we can do here? First, just adjust the ec value here first. Let us see, ec to infinity, 4 pi into 2mn star divided by h square to the power 3 by 2. Okay, so now see here, this is what? E minus ec. How much is this? Eta kt. Okay, square root of eta kt. Okay, eta kt into e to the power, first of all, e to the power, see here, e I am adding what? ec. Okay, adding ec and subtracting ec minus ef in order to balance out this condition, so that we can make e minus ec. Okay, for that purpose I have added what? ec, and I have subtracted ec. Okay, so divided by kt. Now see here, we will get n naught is equal to what? ec to, now see here limit when lower limit is equal to what? When e is equal to ec, then eta is equal to 0, then lower limit will be equal to 0. See here, lower limit will become 0. Okay, 0 to infinity. Now see here, 4 pi 2mn star divided by h square to the power 3 by 2. Okay, to the power 3 by 2, square root of eta kt, into just see here, e minus ec, you have to keep this inside, and ec minus ef you have to take this outside. Okay, see, ec minus ef, take this outside, ec minus ef. Okay, ec minus ef by kt, this is one factor, and another is what? E minus, see here, e minus ec by kt. Okay, into de is how much? kt into kt into d eta. Okay, so now see here, n naught is equal to what? Integration 0 to infinity. Now what we will do here, see here, kt, root kt. Okay, this is what? Root kt, this is kt. How much root kt into kt is nothing but kt to the power 3 by 2. Yes, kt to the power 3 by 2. Then what we will do here, kt to the power 3 by 2, take this inside, then what will come here? 2mn star. Just okay, we will separately we will do it. Okay, so 2mn star divided by h square to the power 3 by 2 into, if you see this is my kt. Which one kt? This kt. Okay, this kt into square root of kt. Okay, so this is what root theta into e to the power minus ec minus ef by kt. Okay, just okay. And if you see here, now see here, e minus ec by kt is how much? Eta. So e to the power minus eta d eta. Okay, d eta. Whatever constant value is there, take it outside. Okay, so that is what, now we are taking this whole constant outside. That will come 4 pi into, see, kt into root kt is nothing but 3 by 2. Take this inside, that is 2mn star into kt divided by h square. Okay, so to the power 3 by 2. Now see what we have taken this factor inside, because its power is also 3 by 2. Okay, so now inside and into e, this is also constant, so this is what ec minus ef by kt. Okay, ef by kt into inside integration is what, this root theta. So where is root theta? So this is root theta here, is root theta. Okay, root theta. Now let us take this root theta into e to the power minus theta d eta. Okay, so now this is what, this whole factor is constant, and we are left with this. Okay, so this is what, this is nothing but gamma function. Yes, you know very well, this is what gamma function. So now where we have to go, let us rub this. Okay, so now see here, so this is what we have reached up to this point. Okay, so what you do, just we are solving this factor. Okay, so this is my equation number, let us say this is my equation number 3. Okay, equation number 2, this is my equation number 2. Okay, equation number 2, I am seeing this factor only, this factor. Solve this integration 0 to infinity e to the power minus eta into square root of eta d eta. Okay, so what is this? Is nothing but, you can write it as eta to the power 1 by 2. Okay, so which is nothing but, if you see e to the power, this is gamma function. What is the value of gamma? Value of gamma is nothing but, if you see here, n minus 1 is equal to 1 by 2. Okay, so this is d eta. Okay, so this is nothing but gamma function. If you will see here in mathematics, what is there? 0 to infinity e to the power minus x into x to the power n minus 1 dx. Okay, so which is nothing but what, if you see n minus 1, so this is nothing but gamma n. Yes, gamma n. So similarly here, if you see here, d eta n minus 1, how much is there? N minus 1 is equal to 1 by 2. That is n is equal to 3 by 2. Means it is gamma 3 by 2. Yes, this is gamma 3 by 2. Okay, so this is gamma 3 by 2. So then this is gamma 3 by 2. Okay, by this expression we can see, we can find this value, n minus 1 is equal to half and n is equal to 3 by 2. So here its value is gamma 3 by 2. Okay, so value of this is what, gamma 3 by 2. This is what, gamma 3 by 2, which is nothing but 3 by 2 minus 1 into gamma 1 by 2. Yes, what is this? 1 by 2 gamma 1 by 2. Yes, which is nothing but 1 by 2 gamma 1 by 2 is nothing but root pi. Yes, this is what, root pi. Now I am going to rub this. Okay, so let us see here what we will get. Now see here, from this is what, n naught, this is n naught is equal to what, n naught is equal to 4 pi, this is 4 pi into 2mn star kt divided by h square to the power 3 by 2. Okay, into 3 by 2 into. Okay, so this is what is this value? This is nothing but root pi by 2. Yes, root pi by 2. Now see here, e to the power minus ec minus ef by kt, ec minus ef by kt. Okay, so now into what we got from here, this solution of this integration is nothing but root pi root pi by 2, root pi by 2. Now see here, n naught is equal to what? 2 will get cancelled. This is nothing but 2 pi into. Okay, so this is 2 pi. Let us see, this is root pi, this is pi, so it is pi root pi. Yes, pi root pi into 2mn star kt, 2mn star kt divided by h square to the power 3 by 2. Yes, 2 to the power 3 by 2. Now see here, 2 root pi, pi root pi is nothing but pi to the power 3 by 2. So it will come inside. It will come inside. So then it is what? It is nothing but 2 into 2 pi mn star kt, mn star kt divided by h square to the power 3 by 2. Yes, to the power 3 by 2 into what? ec minus ef by kt. And finally we can say that n naught is nothing but what? N naught is what? This. Okay, so n naught value is nothing but 2 into 2 pi mn star kt, mn star kt divided by h square to the power 3 by 2 into e to the power ec minus ef by kt. Yes, ec minus ef by kt. So therefore here what you can say, this is my constant factor. So this is nothing but nc into e to the power minus ec minus ef by kt, Okay, so this is my final thermal equilibrium concentration of electron. Okay, equation number 3. So this is the way of what? Doing whole derivation, because we are understanding each and every parameter of this. Okay, how it is. Okay, so this is deriving this whole derivation means we are understanding each and every point. Okay, so no matter, it is not important for your exam, but the concept clarity will come through this only. How each and every, what is this and what is the relation between this thermal equilibrium concentration of electron and Fermi energy level, temperature, everything. If you will thorough with once with this all this derivation, and definitely it will get benefit for you, because as we know very well, how when it is valid, this is valid only under what? Under the condition when ec minus ef is what? When ec minus ef is at least 3 times of kt. Yes, 3 times of thermal voltage. If we see under room temperature, then ec minus ef is ec minus ef must be at least 78 milli electron volt. Okay, so otherwise it is not valid. So we have to deal with the Fermi direct distribution function as it is, and we can't remove that factor of 1 from denominator. Okay, so this is valid only this condition. Okay, this is Boltzmann approximation condition. Okay, so when ec minus ef is at least 3 kt, 3 times of kt. Okay, so I will write here is valid only when when e when ec minus ef is at least 3 times of kt. Okay, so kt means temperature can be anything. It may be 300, it may be 400. At any temperature, if this condition is satisfied, and then you are able to take this approximation. Okay, otherwise not. So let us see for whole concentration. This is for what? Thermal equilibrium concentration of electron. Okay, so now we will see the thermal equilibrium concentration of a whole. Yes, similar. Okay, so there is some difference is there. There is hole and there is electron. Otherwise everything is same. So let us see thermal equilibrium concentration of hole. Just wait. Okay, let us see now thermal equilibrium concentration of what? Hole. Okay, thermal equilibrium concentration. This is what? Thermal equilibrium thermal equilibrium concentration, thermal equilibrium concentration of whole. Okay, thermal equilibrium concentration of whole, thermal equilibrium concentration of whole, this is nothing but P naught. Okay, P naught. So this means what? Thermal equilibrium concentration of whole means total number of hole that is available, total number of hole that is available in the valence band, in the valence band. Where? In valence band. Hmm? Where? In valence band per unit volume, per unit volume. It may be per cube meter, per cube centimeter. Okay, so let us see here. This will come only by integrating the equations that we have found in last class. Okay, what is that equation? Is nothing but that is the distribution of what? Distribution of what? Thermal, that is distribution, equal distribution of whole. Okay, equilibrium, that is what? Equilibrium distribution of whole in valence band. What is that equilibrium distribution of whole in valence band? That is nothing but P of E. Yes, P of E. So P of E is the what? Equilibrium distribution of whole in valence band, which is given by the product of what? If you see the product of density of what? Density of state function. Density of state function in valence band and what? Density of state function in valence band and Fermi Dirac distribution function. That is 1 minus f of E. Okay, so 1 minus f of E, it is nothing but this is the probability. What? This is the probability that the given quantum state is what? Occupied by whole, or you can say it is the probability that the given quantum state is not occupied by the electron, not occupied by the electron. Okay, so this is P of E. Now how we can get the total number of hole concentration, which is nothing but thermal equilibrium concentration of electron and hole. So which is given by P naught is equal to, by integrating this equation over the entire valence band energy, over the entire valence band energy. That is P of E into D of E, P of E into D of E. If you will see here this is my valence band. Okay, so this is my valence band. This is my valence band, and here so many energy level is there. Okay, and somewhere here Fermi energy level is there. Fermi energy level is there, and it is the top of what? Top of the valence band. This is my top of the valence band. Okay, top of the valence band. If you will see here, the bottom means bottom down. How much? What is the limit of lower limit? What is the lower limit possible? That is minus infinite. Lower limit possible here is minus infinite, and upper limit possible is EV. So it will go from minus infinite to EV. Okay, P of E, D of E. So which is nothing but equal to integration minus infinite to EV, GV of E is given by what? As similar, exactly same as what for electron, but here it is hole. Okay, so that's why it is nothing but 4 pi. So this is 4 pi into 2 m. Now it is P star, MP star, effective mass of hole, MP star divided by h square to the power 3 by 2, okay. So to the power 3 by 2 into square root of EV minus E, because which one is the top? EV. Now EV is the top, and this energy level is below EV, so that's why it is what? EV minus C. What? EV minus C. So now see here, EV minus C, and this 1 minus f of E. See, 1 minus f of E is what? Which is nothing but 1 minus, just put the value of f of E is nothing but 1 by 1 plus e to the power E minus EF by kT. Yes, by kT, that we know. Now just solve this. 1 plus e to the power E minus EF by kT, yes, minus 1 divided by 1 plus e to the power E minus EF by kT. Okay, so now 1 will get cancelled, and we are left with what? We are left with E minus EF by kT, EF by kT divided by 1 plus e to the power E minus EF by kT. Okay, so now when you will take this down, when you will take this in denominator, then we will get what? We will get 1 by 1 plus, this will get cancelled. Okay, so 1 plus e to the power, what is e to the power minus. Okay, when you will take this in denominator, it will come in inverse. Okay, so that is what minus ef by kt, or you can say this is nothing but 1 by 1 plus e to the power ef ef minus e by kt. Okay, so ef minus e by kt. So see here what what we what we get here for this 1 minus f of e is nothing but 1 by 1 plus 1 by, this is nothing but 1 by 1 plus e to the power ef minus e by kt. Okay, into d, kt into d. Okay, so now see here p naught is equal to what? If you see here also, now we are going to apply Boltzmann approximation condition. Okay, so if you see here what the energy level ev, if you see ev is at upper level. Okay, and e is at lower level, so e is less than what? ev, e is less than ev. Okay, so e is less than ev, and here if we assume that ef minus e is much greater than kt, ef minus e is much greater than kt. Okay, so then we can say that 1 plus e to the power 1 plus e to the power what? E to the power ef minus e by kt is approximately equal to Boltzmann approximation, that is e to the power ef minus e by kt. Yes, a by kt. Okay, so this is my Boltzmann approximation under the condition of this ef minus e. Okay, ef minus e is much greater than kt. Okay, much greater than kt, or you can say ef minus e. Okay, ef minus e or ef minus ev. Ef minus ev is greater than what? kt. Okay, so this is what condition, ef minus ev is much greater than kt. How much greater than? It is at least what? At least 3 kt. How much? At least 3 kt. ef minus e is at least 3 kt. If it is this, then we are able to take the Boltzmann approximation. Okay, we are able to take Boltzmann approximation. Now see here, p naught is equal to what? Now p naught is equal to minus infinite to ev, and just put this all value 4 pi into 2mp star divided by h square to the power 3 by 2 and see here square root of ev minus e into e to the power minus ef minus e by kt de. Okay, so now we are going to put what? Value of eta. Okay, value of, let us put this value of eta is equal to what? Eta is equal to ev minus e by kt. ev minus e by kt. Okay, value of eta. So now value of eta, then d eta is equal to what? D eta is equal to minus de what? De by kt de by kt. So now which implies that de is equal to what? D is equal to minus kt d eta Okay, so now just put all this value. What we will get? We will get p naught is equal to minus infinite. Just put here e is equal to minus infinite, it becomes plus infinite. Yes or no? This is negative, positive. So this is plus infinity and ev. Just put value of ev here, it becomes 0. Okay, infinity to 0. Integration is infinity to 0, and here it is 4 pi into 2mp star divided by h square to the power 3 by 2. Square root of ev minus e is nothing but square root of eta kt. Okay, so now e to the power e minus ef. Now here we are adjusting the value of ev. Okay, just adjust the value of ev. Just ef plus ev plus EV minus EV plus EV minus EV minus E by KT, okay, into d eta value of d is how much, into minus KT into d eta, okay. So now see here P naught is equal to what? P naught is equal to what? This is minus. Yes, minus sign is there. This minus sign will change the limit. Yes, this minus sign will change the limit, and this limit become 0 to infinity. Yes, 0 to infinity because of this negative sign. Okay. So now see here 4 pi into 2 mp star. Now see here 2 mp star. This is KT. This is root KT. Root KT is nothing but 3 by 2. This also will come inside. So I am writing here KT. Okay, how it came in KT inside it, because root KT is nothing but KT to the power 3 by 2. So it will go inside. So this is h square to the power 3 by 2. Okay, so now at outside this is what integration. Now separate out this. Just take this EV minus EF separately. EV minus EF, okay, and EF minus EV separately. So EF minus EV will come this side, EF minus EV by KT, into see here EV, then minus EV minus EF by KT. Yes, EF by KT. Okay, KT that we have taken inside, and then here is root eta. D eta, okay, so root eta d eta. So now we are coming this side, okay, so let us rub it. Now we are somewhat far away, so from our solution, so this is d eta, and now what we will do here, just take the constant, whatever the term is constant, take that outside, then we will get P naught is equal to 4 pi P naught is equal to 4 pi into 2 mp star KT divided by h square to the power 3 by 2 and into e to the power minus EF minus EV by KT. Okay, that everything we have taken outside, and inside integration is what, 0 to infinity. We are left with this. Okay, what is this? E to the power minus eta and this is eta to the power 1 by 2 d eta. Okay, so now see here P naught is equal to 4 pi 2 mp star KT divided by h square to the power 3 by 2. Yes, to the power 3 by 2 and into e to the power minus EF minus E by KT into, as we have seen in last case, value of this is a gamma function and it is eta to the power 1 by 2. Okay, its value is actually gamma n, value of this gamma function. This is gamma function. This is value of this is gamma n. What is n? Here if we compare this, n minus 1 is equal to 1 by 2, then n is equal to 3 by 2. Yes, it is a gamma 3 by 2. Yes, so this value is gamma 3 by 2, means gamma 3 by 2 is nothing but that we have said 1 by 2 into root pi. Yes, so its value is root pi divided by 2. Yes, divided by 2. Now see here 2 will get cancelled. From here we are left with P naught is equal to what? 2 pi. P naught is equal to what? 2 pi. Now see here 2 pi and here root pi 2 pi into what? Into 2 mp star KT divided by h square to the power 3 by 2 into e to the power EF minus E by KT. Yes, KT. So this is the value. Okay, so now take this pi root pi inside, because this is also same, its power is what? Pi to the power 3 by 2. This is also 3 by 2. Just take this inside. So we will take this inside and we are now left with final answer. That is what? This is nothing but 2 pi mp star. Okay, this is pi root pi is nothing but to the power 3 by 2. Yes, pi to the power 3 by 2. That's why I am taking this inside. Okay, 2 pi mp star kt divided by h square to the power 3 by 2. Yes, 3 by 2 into minus ef minus e by kt. Yes, ef minus e by kt. So therefore here p naught is equal to what? Nv. This is what? Value of Nv. Yes, Nv e to the power minus ef minus e by kt. Yes, by kt. So this is my thermal equilibrium concentration of whole. Thermal equilibrium concentration of whole, and here Nv is what? Nv is density of density of state function. Density of state function. Yes, density of state function. Density of state function in valence band. Yes, valence band, or you can say density of quantum state in valence band. Okay, so this is my whole concentration. This is my what? Thermal equilibrium concentration of whole. Thermal equilibrium concentration of whole. When it is valid only when EC minus, when what? When EF minus EV. When this EF minus, yes, just wait. But what we did here, EF minus EV. Yes, so this is what? Sorry, this is EF minus EV. Okay, EF minus EV. This is EF minus EV. EF minus EV. Okay, so this is EF minus EV. EF minus EV. When it is valid only when this when Boltzmann approximation is valid. That is valid only if EF minus EV is what? At least 3 times of KT. 3 times of KT. Okay, so now we have completed both of thermal equilibrium concentration for electron as well as hole. Okay, so that's all for this. Okay, so we have derived two equations for electrons and hole under thermal equilibrium. Okay, under thermal equilibrium. Okay, concentration of electron and hole. So concentration of electron and hole, the resultant, if I will give you conclusion about this, what is the final conclusion? Final conclusion that we got from here, from these two derivations for electrons and hole, that is what? Electron and hole. See, finally electron and hole. Okay, so thermal equilibrium concentration of electron and hole. First for electron, what we got for electron? N naught is equal to what? N naught is equal to what we got here? Nc. N naught is equal to Nc e to the power minus Ec minus Ec minus Ef by Kt. Yes, Ef by Kt. So this one equation, we got this equation for thermal equilibrium concentration of electrons, and another is what? Thermal equilibrium concentration of hole, that is Nv e to the power minus Ef minus Ev by Kt. Okay, so these two equation, where Nc and Nv is what? Where Nc and Nv is what? Density. What? Density of quantum state. Okay, density of state function. Density of state function, you can say density of state function in conduction band. Density of state function in conduction band, and density of state function in conduction band and valence band. Yes, density of state function in conduction band and valence band, or you can say these are the density of quantum state. What? Density of quantum state, where in conduction band and valence band. Okay, what are those quantum state? These are nothing but these are discrete energy state, where exactly the electron is sitting. Okay, where exactly the electron is sitting. Okay, so this is actually the place, this is actually the room of electron. Okay, this is actually the place or location of electron, or in general or in layman language we can say this is the constant, this density of state function. These are nothing but density of what? Density of location of electron in both conduction band and valence band. Okay, conduction band and valence band. If we see for Nc and Nv value, okay, Nc and Nv value for silicon, germanium and gallium arsenide, and effective mass value, okay, effective mass value. And see here we have also taken what assumption that the Fermi energy level is in between, is in what, where in between energy band gap. Okay, so there these are valid only under the assumption of that the Fermi energy level that is lying in between energy band gap. Okay, within the energy band gap. Okay, and other condition is our Boltzmann approximation, for which these both gap must be at least 3 times of kt, then only it is possible. Otherwise we have to deal with what original Fermi direct distribution function. Okay, in that case we can't remove that one factor in denominator. Okay, so that is for thermal equilibrium concentration of electron under one assumption and one approximation. Okay, so now we will see some value of for what Nc and Nv value. These some value for effective mass, and value for density of state function. Okay, for what? For first for silicon, then for gallium arsenide and germanium. Okay, so germanium. So what we will see here for this we are going to see here Nc, density of state in conduction band, density of state in valence band, and this density of state in valence band, and this is ratio of effective mass of electron to its rest mass. Yes, similarly here effective mass of hole to rest mass. Okay, so for silicon, if you see Nc, for silicon Nc is nothing but 2.8 into 10 to the power 19 per cube centimeter. So let us write this is in centimeter cube, this also in centimeter cube. Okay, both are in centimeter cube. This is 2.8 into 10 to the power 19. This is 1.04 into 10 to the power 19. Mn star by m naught star. Here is 1.08 ratio of this is what 1.08, and this is nothing but 0.56. Mt star by m naught star. Okay, so and gallium arsenide, if we see this is 4.7 into 10 to the power 17, and Nv density of state in valence band, that is 7 into 10 to the power 18, and Mn star by m naught star ratio is 0.067, and Mt star by m naught ratio is 0.48. Similarly for germanium, Nc density of state in conduction band is 1.04 into 10 to the power 19 per cube centimeter. Nv value is Nv density of state in valence band is 6 into 10 to the power 18 per cube centimeter. Mn star by m naught star value here is 0.55, and Mt star by m naught value is 0.37. Yes, these are the some constant value for Nc and Nv. Okay, so that's all for this. Okay, for this lecture, that is about the thermal equilibrium concentration of electron and hole. Okay, so that we have done, and which we have taken under one assumption and one approximation. What is assumption? Assumption that we have taken that the Fermi energy level lies within the energy band gap, and the approximation that we have taken is valid only when EC minus when the gap between top of the valence band and Fermi energy level and bottom of the conduction band and Fermi energy level is at least 3 times of kT, then only Boltzmann approximation is valid. Okay, so thank you very much. Okay, so thanks.